Hello friend, today we will talk some important problems from integral equations for upcoming examinations like CSIR UGC NETs set. Okay, and if you missed out my previous video on integral equations, so I recommend you please watch my previous video. Okay, now the question number one is find the iterated kernels k and xt of the following kernels. Kxt is x minus t, where the lower limit is 0 and upper limit 1. Number 2, kxt is sin x minus t, when the lower limit is 0 and upper limit is pi by 2. For n equal to 2 and 3, that is, we have to find out the iterated kernels k2xt and k3xt. That's all. Okay. Third, kst is similarly like sin x plus t, upper limit pi and lower limit is 0 for n equal to 2 and 3. And last, kxt is t, where a equal to 0 and b equal to 1. Okay, so there are 4 questions to find out iterated kernels. Okay, and there are many more problems. Okay, so first of all, I try this. Okay, and you try all these problems. Okay, if you have any problem of these questions, then you can comment, and in the next video I will provide the solutions. Okay, so let's try these questions. Okay, so the problem is kxt, this is x minus t, and the lower limit is 0 and the upper limit is 1. Okay, so we know that k1 of xt is nothing but kxt, this is number 1, and number 2 is kn of xt, this is integration over a to b kxz kn minus 1 zt dz for n equal to 2, 3, 4 and dot 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 dot. Okay, so first of all, so k1 of xt, this x minus t. Okay, no problem. So now k2 of xt, this is integration over a to b, so 0 to 1, 0 to 1 k of xz k1 of zt dz. Okay, so this is integration over 0 to 1, this is x minus z, this is z minus t dz. Okay, so this is, if you multiply this, so you get xz minus xt minus z square plus zt dz, and this can be written as integration number 0 to 1. If you common z, then you can get this minus xt minus z square dz. Okay, so this is z square by 2 x plus t minus x2z minus z cube by 3 0 to 1. So this is nothing but x plus t by 2 minus xt minus 1/3. Okay, no problem. Next, k3xt, this is integration over 0 to 1 k of xz k2 of zt dz. Okay, this is integration over 0 to 1, this is x minus z, and this is, since this is k2 of x2 is this, so k2 xz is nothing but z plus 2 by 2 minus zt minus 1/3 dz. Okay, so Now I can multiply this. So first of all, we arrange like this: z by 2 t by 2 minus zt minus 1/3 dz. Okay, so this is indication 0 to 1, and if we multiply it by x, so this is xz by 2 xt by 2 minus xzt minus x by 3, then by z, so minus z square by 2 minus zt by 2 plus z square t minus z by 3 dz. Okay, now this can be written as indication was 0 to 1 z x by 2 minus xt minus t by 2 plus 1/3 minus z square half of minus t, and if we common x, so t by 2 minus of 1/3 dz. Then we integrate, so we get z square by 2 x by 2 minus xt minus t by 2 plus 1/3 minus z cube by 3 half of t, and x t by 2 minus 1/3 z was 0 to 1. If we put the value of z to 1, so we get half of x by 2 minus xt minus t by 2 plus 1/3 minus 1/3 half minus t, and then x t by 2 minus 1/3. Okay, and the if we put the value of z, so all are the 0. Okay, so this is x by 4, and here minus x by 3. Okay, now xt by 2 and xt by 2 are cancel out. Okay, and minus t by 4 here this, and here plus t by 3. Okay, and plus 1 by 6 minus 1 by 6 are cancel out, so only this is minus x, and this is t, so we get minus of x minus t by 12. So this is minus 1 by 12 x minus t, and x minus t is nothing but k1 xt. Okay, so k1 is x minus t, k2 is x2 is this, and k3 of xt is this. Okay, similarly k4 xt is can be written as indication of 0 to 1 k of xz k3 of zt dz. So this is indication of 0 1, this is x minus of z, and this is minus 1 by 12 k1 of zt dz. This is indication, this is minus 1 by 12 0 to 1 x minus z and z minus t dz. This is nothing but k2 xt. Okay, similarly k5 xt is nothing but minus 1 by 12 k3 xt, and this is written as minus 1 by 12 square k1 xt. Similarly k6 xt written as this. So this is written as minus 1 by 12 square k2xt. Okay, if n is odd, then we get express as k1. If n is even, it can express as k2. Okay, so the value of the integral is, if n equal to 2m, so k2mxt is nothing but minus 1 by 12 m minus 1 k2xt. Okay, and if n equal to 2m minus 1, so k2m minus 1 xt is minus 1 by 12 m minus 1. This is k1 xt. Okay, if you put this value, so you get minus 1 by 12 to the power m minus 1, and this is x minus t. Okay, so where m equal to 1, 2, 3 etc. Here if we put the value, so we get k2xt, k2mxt. So there are iterated kernels, two iterated kernels, one for even and one for odd. Okay, if we put the value of k2xt, that is, this is expressed as this, and k2xt is this something x plus t by 2 minus 1/3 minus xt. Okay, this is our even iterated kernels, and this is our odd iterated kernels. Okay, there are two iterated kernels. Okay, this is the method. Similarly, you can try this problem, that is kernel is t and lower limit is 0 and upper limit is 1. So kxt is t, lower limit is 0 and the upper limit 1. So we can write k1 of xt, this is t. So k2 of xt equal to 0 to 1, k of xz, and k1 of zt dz. So this is integration over 0 to 1, this is z, and this is t dz. So this is nothing but t integration over 0 to 1 z dz. So this is t into half. Okay, that is t by 2. Similarly, k3 of xt equal to integration over 0 to 1 k of xz, k2 of zt dz. So this is integration over 0 to 1, this is z, and this is t by 2 dz. So this is t by 2 integration over 0 to 1 z dz. So this is t by 4, that is t into half square. Now k4 xt, this is integration over 0 to 1 kxz and k3 of zt dz. So this is 0 to 1, this is z, and this is t into half square dz. So this is can written as q. Okay, so similarly you can write knxt when 4 and the power is 3. So this is t into half to the power n minus 1. This is our iterated kernels. Okay, next, now you can try the b and the c. Okay, now our next problem is find out the resolvent kernels of the integral equations. Okay, so first of all, yx, this is f of x, this is k of xt, this is y dt. Second option, yx equal to x square, indication of 0 to x e to the power x minus 2 y dt. In each case, in each of the problem, first find out the iterated kernels and then resolvent kernel. Okay. Then option D is yx equal to 1 plus indication of 0 to x yt dt. And option E is yx equal to x, indication of 0 to x t minus x yt dt. So here the kernel is t minus of x. Next, if in these questions the kernel is 3 to the power x minus ft, and the next is xt, and the next one is e to the power x square minus t square, and the next cos hyperbolic x by cos hyperbolic t, and the next one, that is j, is t. There the kernel is t. Okay, so this is our problems related to resolvent kernels. Okay, I can try only one problem and then others you can try. If you have any problems from these questions, and then you comment in which question I can solve, and then in the next video I'll provide the solutions. Okay, so I can try this B. Simple questions. Okay, so yx equal to x square, indication on 0 to x e to the power x minus t yt. In each questions, first find out the iterated kernels and then resolvent kernels. Okay, so first of all, k1 of x, this is nothing but e to the power x minus t. Okay, k2 of xt, so this is our Volter integral equations. So integration over t to x k of xz k1 of zt dz. So this is integration over t to x, this is e to the power x minus z, and this is e to the power z minus t and dz. So this is integration over t to x e to the power x minus t dz. So e to the power x minus t z over t to x. So this is e to the power x minus t of x minus t. Now k3 xt is integration over t to x k of xz and k2 of zt dz. So this is integration over t to x kxz, this is e to the power x minus z, and k2 this e to the power z minus t of z minus t dz. So this is integration over t to x e to the power x minus t of z minus t dz. So this is expressed as this. If we integrate with respect to z, so we can get z minus t square by 2 over t to x, like this. Okay, so this can be written as, if we put the value of x, so this is x minus t square by 2 minus 0. So that is e to the power x minus t square by 2. So this is our k1 xt, this is k2 xt, k3 xt. So similarly kn xt, this is nothing but e to the power x minus t x minus, when 3 then power is 2, so this is n minus 1, and this is nothing but n minus 1 factorial. If we also find out k4, then we get e to the power x minus t cube by 6, and 6 can written as 3 factorial. So this is n minus 1 factorial. Okay, so the resolvent kernel with respect to lambda is 1, with respect to lambda 1, so we get, so r x t with respect to 1, we know that this is a series, infinite series, lambda to the power m minus 1 km xt. So this is written as summation m equal to 1 to infinity, this lambda is 1, so only km of xt, that is k1 xt, k2 xt, and similarly others. So this is e to the power x minus t, this is x minus t e to the power x minus t, then x minus t square by 2 factorial e to the power x minus t, and similarly the other terms. Okay, if we common e to the power x minus t, then we can get 1 x minus t, x minus t square by 2 factorial, and similarly others. So this is a known series. This is nothing but e to the power x minus t, so we can get e to the power 2 of x minus t. So this is our resolvent kernel, okay, corresponding to lambda equal to 1. So obvious. Okay, then in the second case, option C, here e to the power t minus x. Okay, option B, x minus t, and here e to the power t minus x. Similarly, we can get this e to the power t minus x, e to the power x minus t. Then we can get e to the power 0, that is 1. Okay, so here answer is 1, here e to the power 2x minus of t. Similarly for others, then you can try this problem. Okay, if you have any problem, then comment and I will provide the solution in the next video. Okay, next this is this. Okay, question number 3 is find the eigenvalues and the eigenfunctions of the homogeneous freedom integral equations. There are 4 questions. Okay, I'll provide the solutions in the next video. Okay, this video is very long, like 30 minutes or above. Okay, some special problems and with this very important for your examinations. You only remember this. Okay, not to try to solve these questions in examinations. Okay, this is a huge question. Now the question is yx equal to lambda integration over 0 to pi kxt yt dt. Okay, where the kernel is defined below cos x sin t and cos t sin x over 0 less than x less than equal to t and t less than equal to x less than equal to pi. Okay, whenever the kernel given this, then we can write the eigenvalue directly. Okay, so there are 2 methods. We use Leibniz rules 2 times to get the Sturm-Liouville problems, and then put the values of lambda. There are 3 cases: lambda equal to 0, lambda greater than 0, lambda less than 0. Okay, to get the Sturm-Liouville problem. This is very huge. Okay, this is for yours. Okay, so whenever the kernel is this, the corresponding eigenvalue is lambda n 1 minus n plus half square yn, that is the eigenfunction is cos n plus half x. Okay, for n equal to 1 2 3 and dot. In the second questions, when the kernel kxt is sin x cos t, where 0 less than x less than equal to t, and sin t cos x for t less than x less than equal to pi, then we write directly eigenvalue as lambda n equal to n plus half square minus 1, and eigenfunction is sin of n plus half x, where n equal to 1 2 3 dot. Okay, whenever the kernel is this, we can directly write these eigenvalues and eigenfunctions. Okay, number 3 and number 4, easy, very easy. So you can see that whenever kernel kxt is xt minus 1 and tx minus 1 over 0 to t and t to 1, then the corresponding eigenvalues is this, and this is eigenfunctions. And number 7, and whenever kxt, that is our kernel, is tx plus 1 and xt plus 1 over 0 to 1. So there are interesting, this is interesting, lambda 0 is 1 and the corresponding eigenfunction is e to the power x. And there are also infinitely many eigenvalues, lambda n minus n square pi square, and the corresponding eigenfunctions n pi cos n pi x plus sin n pi x, n equal to 1 2 3 this. Okay, so this is the best problems for integral equations. Okay, and every year for CS revision, and you can see that this is this problem can given in that 2016 in December or June maybe. Okay, and this problem this is given in 2018 June. Okay, this problem in short times in examinations, in our examinations there are restricted times, so we cannot go further the process. Okay, so we can only remember this. Okay, or memorize this. Whenever kernel this, eigenvalue this. Whenever kernel this, eigenvalue this. Okay, now there are some important theorems. Okay, first of all, a kernel kxt is symmetric whenever kxt is k bar tx, or k bar this is conjugate. Like if kxt is tx, so then ktx this is x, this is their same, so this is real symmetric kernel. Okay, so a kernel kst is a symmetric if kxt this is ktx. And and also you can say that a kernel kxt is called a real kernel kxt is called symmetric, then kxt is ktx. Okay, first of all, the first theorem is if a kernel kst is symmetric, then all iterated kernels are also symmetric. This is obvious, that is knxt. If kst is symmetric, then all iterated kernels are symmetric. Okay, next theorem, this is Hilbert's theorems, say that if a kernel kxt is real, symmetric and not identically zero. Okay, first of all, real, symmetric and not identically zero, then it has at least one eigenvalue. Eigenvalue or characteristic value or characteristic number, all are same. Okay, number 3, the eigenvalues of a symmetric kernel are real. Okay, the eigenvalues of a symmetric kernel are real. Okay, the last is the eigenfunctions of a symmetric kernel corresponding to different eigenvalues are orthogonal. This is important. Eigenfunctions but corresponding to different eigenvalues are orthogonal. Okay, so this is based problems for integral equations. Sorry, so this is base problem for integral equations. In the next video I'll provide the solutions of this eigenvalue. Okay, and in questions you can find out these problems, and there are more problems like this, iterated kernel, resolvent kernels. Okay, you can try this at home. Okay, at home or else. If you like this video, subscribe my channel and share with your friends. Okay, and if you have any problem from these questions, then comment, and in the next video I'll provide the solutions of the eigenvalue and eigenfunctions, and the questions that you cannot solve. Okay.